Professor R. Ashokamani, Director, Research and Development, Dhanalakshmi College of Engineering, Tambaram, Chennai. He is former professor and head of the department, Physics, Anna University, Chennai. He is presently guiding 3 research scholars. He has more than 44 years of UG and PG teaching experience and 33 years of research experience. 14 research scholars have obtained doctorate under his guidance in the area of material science and solid-state physics. He has more than 150 research publications to his credit, of which 90 are in international journals. He has authored a book on solid-state physics, which is an international publication. He has participated in several international conferences, both in India as well as in foreign countries such as USA, UK, France, Germany, Italy, and Yugoslavia. He has been a guest scientist at ICTP, Italy, several times. He is a fellow and treasurer of Tamil Nadu Academy of Sciences.
Welcome to the UGC lecture series. Now we are going through the chapter on optics under paper 14. Now the first paragraph, which refers to geometrical optics, goes as follows. The Fermat's principle, optical path, these things we have seen already. Now in today's lecture we will see them lenses, transverse magnification of a spherically refracting surface, Lagrange and Helmholtz laws of magnification. The other things we will see in the lectures to come. So we will talk about lecture 2 under geometrical optics. The contents are refraction at a spherical surface, principle foci, Smith-Helmholtz equation and Lagrange law. We will start with refraction of light at a spherical surface. Let us assume that a monochromatic light starts from the object O. You have the object here. It is incident on a spherically refracting surface. This is a surface here, and you can assume this to be air. The medium in which the object is placed is an air of refractive index mu1, and this is a medium, right? The whole thing is a medium, and the refractive index of this medium is mu2, as you will be seeing later, and the image is obtained at the point I. I is the image, O is the object, and what is R? R is the radius of curvature. What is meant by radius of curvature? You know, a surface, any spherical surface can be imagined as a part of a sphere. You have got a surface here, you can complete it, you will be getting a sphere, and you will be having the center of the sphere, and here this C refers to the center of such a sphere. You can have this arc, you complete the circle, right? You complete the circle, you will have a circle. Or if you have got a 2-dimensional thing, the surface, you will have a spherical surface in the circle, and the center of the sphere, see the center of the sphere, right? This is a surface, spherical surface. This forms sphere. The center of the sphere is found at the point C, and the distance that separates P and C, the center of this point P and C, that is the so-called radius of curvature, or is the radius of curvature. That will come in the Smith-Helmholtz relation. In all the relations, when we are talking about refraction through lenses, or that is the radius of curvature of the lens, will come into the picture. And so you have got object here, I here, C the center of curvature, and R is the radius of curvature. And you have to assume that the rays which are incident are paraxial rays. What are paraxial rays? Rays which are almost parallel to the optic axis, they are called paraxial rays. That means the angles alpha, beta, they are all very small. if a ray goes and hits at a surface somewhere here, if alpha is very large, they are called marginal rays. And for the sake of convenience, for mathematical convenience, to obtain a simplified relation, we assume the rays to be paraxial. What do you mean paraxial rays? As I told you, the light rays which are incident on the surface making very small angles. Angle alpha will be small, beta will be small and all. That means the rays are almost parallel to the optic axis. That is important, right? We will be making a paraxial approximation. Where is the object O? The object O is a distance u from the point P, and similarly the image I is at a distance v from the point P. There are distances u and then v, and you have got r here, and we will be obtaining relations connecting the refractive index mu1 of this medium and the refractive index mu2 of this medium that you have got here, and u, v and capital R. So, what are the parameters which will be related now? The parameters which will be related are the object distance u, the image distance v, and the radius of curvature of the lens, namely capital R, and the refractive indices mu1 and mu2, that is the where the object is placed, the medium is having a refractive index mu1. The image is obtained in another medium whose refractive index is mu2. And this is again shown here. You have got object here, image obtained here, center of curvature is here, u is the object distance, v is the image distance. And the angles made are shown again here, alpha here, beta here and gamma here, and theta 1 is this angle, theta 2 is this angle. And very important point is this Pm, that is the distance separating P and M, right? M is, what is M? M is the perpendicular drawn from A to the optic axis, point M here, and the height of AM is h, that also will come in the picture. And this Pm will be equal to delta. Now, Pm is delta, and what about the magnitude of Pm? We are going to omit this lambda. Under what approximation delta can be omitted? If Pm is made very small, if Pm is very small, how will you make Pm to be negligibly small? If the xy, that is your spherical forces, instead of spherical, if it is plane, what will happen? Pm will be equal to 0. Is that right? If it is, instead of this being spherical, radius of curvature is very small. If you surface is like this, suppose surface is like this, what will happen? The center of curvature will be found somewhere here. If it is like this, the circle is formed here or sphere is formed here, the center of curvature will be here. If it is like this, then the center of curvature will be somewhere here. If the center of curvature is larger, what will happen? This delta will become smaller. Suppose instead of center of curvature be, instead of a spherical surface, almost you have got a plane surface, Pm will be equal to 0. Is that right? Pm will also, the delta will become equal to 0. So, we will be taking care of delta, and we will make an assumption at a later stage, delta is small and you are going to neglect this delta. At that point, you should remember where is delta. This Pm, the distance that separates P and M is delta, right? It should be assumed to be very small and neglected at a later stage. Using the theorem that an exterior angle, where is exterior angle? You got exterior angle theta 1, right? This is exterior angle. And what are the interior angles? If you look at this triangle OAC, okay, I will be referring to the triangle OAC. So, the theorem states an exterior angle of a triangle equals the sum of the two opposite interior angles. Now, what are the two interior angles? Alpha and gamma, the two opposite. This is the exterior angle theta 1, that will be sum of alpha and gamma, right? Is that right? Now, therefore, you look at this triangle OAC, that is what I am stating here, the triangle OAC. For the triangle OAC, this law is valid, this relation is valid. Theta 1 is alpha plus gamma. Where is theta? This theta 1 here. Theta 1 obviously the exterior angle. that will be sum of the two interior angles, namely alpha and gamma. That is what I am writing here. Theta 1 will be equal to alpha plus gamma. Whereas this gamma, that the angle that you have here, will be sum of the two angles theta 2 and beta here, right? I will be looking at this triangle, that is ACI, right? Now, therefore, ACI is the another triangle for which I can write gamma to be equal to theta 2 plus beta. That is what I am writing here. Gamma will be equal to beta plus theta 2. From the laws of refraction, you all know that sin theta 1 by sin theta 2 will be equal to mu 2 by mu 1. You write generally sin I by sin r is equal to mu. Mu is the refractive index. But here you are having a very generalized relation. Mu 1 is the refractive index of the first medium. Mu 2 is that of the second medium. You write sin mu 1 sin theta 1 is equal to mu 2 sin theta 2. And the tangents of alpha, beta and gamma, the tangent values tan alpha, tan beta, tan gamma, can be written in terms of h, mu and delta. Let us look at the picture again. What are your h is here, as I told you. H is the height of this AM is h, and u is this distance. Remember, OP is u, and you know what is tan alpha? Tan alpha is h by OM. Remember, tan alpha is what? H by OM. What is OM? OM is OP. OP is u, right? Plus PM, right? That is delta. I told you about delta and the significance of delta and what we are going to do with delta, all these things I told you just now. But anyway, for the present, mathematically speaking, what you find is tan alpha will be, tan alpha is this height AM or h divided by OM, where OM is OP plus PM. What is OP? OP is the object distance, u plus delta. That is what I am writing here now. So, tan alpha will be h divided by u plus delta. Okay, this is what I am writing here. Tan alpha is h divided by u plus delta. Okay. Similarly, tan beta, you can write tan beta here, right? Tan beta will be what? This height again h divided by mi, right? Mi is pi minus pm, right? What is mi is pi is the whole distance, right? Pi is v, okay? From v I have to subtract pm. Hope you understand this point. Now h divided by mi. What is mi? Mi is pi minus pm. Pi is v. V minus delta will come in the denominator. That is what I am writing here. So what I do now is v minus delta comes in the denominator. Tan beta will be h by v minus delta. Similarly, tan gamma, you can look at the picture again. Tan gamma, this is a gamma here. And as we did for beta, the angle gamma is here. So tan gamma will be again h divided by mc. H divided by mc. H is here. MC is what? MC is PC minus PM. You have to subtract. PC is R. What is PC? P is the center. C is the center of curvature. So PC will be, if you have got MC, because this is a right angle triangle, and so tan gamma will be H by MC. But MC will be PC minus PM. So PC is your R, right? PC is R. R minus delta will come in the denominator now. H by R minus delta will be equal to tan gamma. That is what I am writing here. Tan gamma will be H divided by R minus delta. Okay. So from the triangles I showed, using the fact that exterior angle will be sum of the two interior angles, I have written down the certain relations. Then I wrote down the values of tan alpha, tan beta, tan gamma. Now, as I told you earlier, we are talking about paraxial rays. By paraxial rays, what I mean is the angle subtended by the rays with the surface of the lens or the second medium. The angles are very small. Therefore, we can make a certain approximation. Let us have a break at this point. welcome back at the break. I have been telling you about the relations that we obtained from this diagram. What we obtained just now are the expressions for tan alpha, tan beta and tan gamma, and we make use of the paraxial approximation. By paraxial approximation, what we mean is alpha, beta, gamma are small. And again, the angles theta 1 and theta 2 also should be assumed to be small. From the laws of refraction, you write mu 1 sin theta 1 to be equal to mu 2 sin theta 2. This is a Snell's law, and this is the relation that we had just now. For paraxial rays, the angles theta 1 and theta 2 are small. We are going to assume all the angles that we are mentioning, alpha, beta, gamma, theta 1, theta 2, they are all small. Hence, omitting the sign of the angles, you write mu 1 theta 1 is equal to mu 2 theta 2. What is it exactly we are having? We write mu 1 sin theta 1 is equal to mu 2 sin theta 2. Instead of sin theta 1, we are going to write theta 1 only. That means we make, when angle theta is small, you make the approximation sin theta 1 tending towards theta 1. You replace sin theta 1 by theta 1. When can you do it? Provided the angle is small. So, because we are assuming the angles theta 1, theta 2 are angles are small, you write mu 1 into theta 1 to be equal to mu 2 into theta 2. Now, you are theta 2 combining this, the above, with the equation 1. What is the equation 1? What do you do? By combining, you get rewrite theta 2, right? So, you have to replace theta 1 by what you have in relation 1. Look at the relation number 1. You have got theta 1. Theta 1 is alpha plus gamma, right? Now, the theta 1 that you are going to have, you are having there, should be replaced by alpha plus gamma. So, theta 1 is, your theta 2 will be mu 1 multiplied by theta 1 divided by theta 2. That is your, okay. Now, your theta 2, I am going to retain theta 2 here. Theta 2 you are retaining, then theta 2 will be equal to what? Mu 1 theta 1 by mu 2, and in the place of theta 1, I am going to have alpha plus gamma. That is what you had earlier. I showed you in the relation. Your okay, that is your theta 1 will be equal to alpha plus gamma. Therefore, you are having alpha plus gamma here. Substituting this in the second equation of 1. Second equation means what? You look at the right hand side of equation 1. The right hand side is gamma, right? This is what we have done just now. Now look at the right hand side of equation. That is the second part of equation 1, that is gamma is equal to beta plus theta 2, right? Gamma is equal to beta plus theta 2. Therefore, in the place of gamma, you put gamma is beta plus theta 2, okay? Substitute that beta plus theta 2, right? You will be having beta plus theta 2. So, this will be equal to mu 1 into alpha plus mu 2 into beta. That will be equal to mu 2 minus mu 1 into gamma. A relation that you are getting now, mu 1 alpha plus mu 2 beta will be mu 2 minus mu 1 into gamma. So, use the approximation. What is the approximation? As I told you, we assume alpha, beta, gamma to be small. Therefore, what we do is you make tan alpha is equal to alpha. We made sin theta 1 equal to theta 1. Sin theta 2 equal to theta 2. When theta 1, theta 2 are small, that can be done. Similarly, the tan alpha, tan beta, tan gamma, they will be made as simply alpha, beta, gamma. And we wrote tan alpha is equal to what? You look at the relation. Tan alpha is equal to h by u plus delta. I told you that we do two things. You replace tan alpha by alpha. Second thing is you omit delta. What is delta? I told you delta will be small. Look at the diagram. This is delta here. If PM is made to be small, that is PM is delta, right? This is the important point. PM is delta. Now, supposing instead of this spherical mirror of this radius of curvature, if R is made to be very large, almost straight, your PM will become 0, right? PM is 0. If it is PM is curvature, the bending is very large, then PM will be large. On the other hand, if it is a straight plane mirror, like and then your delta will vanish. Therefore, you have to make a comparison between R and delta. If R is very large, delta will be very small. Okay, if it is almost straight, delta will be reduced. And what I am going to do now, I am going to say that delta being small, for mathematical convenience, I will be omitting delta. So in the relation that you have here, I write tan alpha is h by u plus delta, and I am doing two things. One is tan alpha I will write as equal to alpha. That can be done provided alpha is very small. When can you have alpha small? For paraxial rays, alpha will be small. Therefore, I will do the first thing, I will replace tan alpha by alpha itself, number one. What is second thing? I will remove delta. I told you why or under what condition delta can be removed. And so, your relation that you have here, tan alpha will become equal to alpha. That delta I will be removing. So, alpha will be equal to h by u. And similarly, beta here, tan beta will be replaced by beta. Beta will be h by v. And gamma will be h by r. That is what I am going to do now. I will be rewriting the relations as alpha is equal to h by u, and beta is equal to h by v, and gamma is equal to h by r. And making these approximations and substituting these things in the above relation involving, I am writing now for alpha, beta, gamma, these things, right? Alpha. So now you write here, what is alpha? Alpha is h by u. What is beta? Beta is h by v. Okay, in the relation h by v. Beta is h by v. That is what that is the reason why I am having, okay, v here, and I am cancelling h throughout, right? And mu2 minus mu1, here, and mu2 minus gamma. Gamma is what? Gamma is h by r. Okay, you will be having throughout h will be there. You can cancel h throughout, that is found in the numerator. And so, the resultant expression that you will be getting now is mu1 divided by mu plus mu2 divided by v. V is the object distance, u is the object distance, and v is the image distance. And that will be equal to mu2 minus mu1 divided by r, and r is the radius of curvature of the surface about which we are talking about. It may be a concave or convex surface. Now apply the sign convention. The sign convention says u is negative, v is positive, and r is also positive. So r is positive and v is positive, u is negative, and so put a minus sign here, right? By this, what will happen is mu2 by v minus mu1 by u, okay, mu2 by v minus mu1 by u will be equal to mu2 minus mu1 by r. This relation that we have got now is known as the Gaussian relation. Though this relation is derived for a convex surface, it is important to realize now we have got a convex surface, and for a real object we get a real image, but it is equally valid for other conditions. That means for a convex surface we have got for a concave surface, and similarly when you get a imaginary, you got a virtual image, under these conditions also the Gaussian relation is valid. So what is the Gaussian relation? Mu2 by v minus mu1 by u is equal to mu2 minus mu1 by r. This is an important relation, Gaussian relation. This relation has been obtained when you study the refraction of light at a spherical surface for a surface that you had, as I shown in the earlier diagram, for a convex surface, and the relation that is obtained is valid whether it is convex or concave, and again whether the image obtained is a real image or a virtual image. For both cases the relation is valid. Okay, that is important. Then you have the first medium. We are talking in general, this is a general relation. Mu1 and mu2, what we had mu1, as I told you, the object is placed in air. So what is refracted into the air is 1. So replace your mu1 by 1. Okay, mu2, now there is no need to distinguish between mu1 and mu2 because mu1 is 1. So mu2 can be replaced by mu itself. Therefore you have the following relation: mu by v, The first medium is here. The second medium is of refractive index mu. In the place of mu2, you have got mu. So mu2 is mu, mu1 is 1. So the above relation becomes gets reduced to, takes a new form, mu by v minus 1 by u is equal to mu minus 1 by r. This is a very important relation, right? This is an important relation that you got here. Okay, this relation should be borne in mind. Mu divided by the image distance minus 1 by u, that is object distance, will be equal to mu minus 1 by r. Okay, this is a relation that of considerable significance. And then now we will talk about the two principal foci that are to be had in mind for our further discussion. Using equation 3, that is equation 3 that you have here, one can determine the first and second principal foci. Now look at this F1, it is the position of the object for which the image lies at infinity. The image will be at infinity. The position of the object for which the image lies at infinity. F2 is the position of the image for the object which is lying at infinity. You have got the object at infinite distance. The light rays coming at from a object at infinite distance, they will all converge, and the image is obtained at F2, right, at a point here F2, and this is called one of the principal, one of the focal lengths, and this is foci, this is another foci. So you will be talking about the two foci. If the object is placed at F1 such that the refracted rays become parallel to the principal axis, and V becomes infinity. The image is obtained at infinite distance, right? The image is obtained at infinite distance. So the object is placed at F1 and the image is obtained infinity. Then using the above relation that we had, right? What is the relation? Mu by V minus 1 by U is equal to mu minus 1 divided by R. Okay, this is the relation we had. So now, or you can have a generalized relation because you are having mu1, mu2. So mu2 by V minus mu1 by U. Okay, mu2 minus mu1 by R. So using this relation, you will be having now V is infinity, right? The image is obtained at infinite distance. The image distance will be infinity. Okay, V is infinity, minus mu1 by F1 will be equal to mu2 minus mu1 by R. Or in other words, F1, one of the principal focus, mu1 multiplied by R divided by mu2 minus mu1. Okay, so you are having, it will become 0, right? Value divided by infinity will become 0. So your mu1 and these things can be, so you get F1 to be equal to, take this form, mu1 multiplied by R divided by mu2 minus mu1. Okay, the position of the axial point object whose image is formed at infinity is known as the first principal focus, and this is called the first principal focal length. F1 is called the first principal focal length. Where is the position of object and image? The position of the axial point object whose image is formed at infinity is known as the first principal focus. Now look at the diagram. The image is formed at infinite distance, right? The image is formed at infinite distance. Okay, this is one of the principal foci, and the second principal foci will be there for the another diagram. We will now pass on to the summary session as of now. Gaussian relation connecting U, V and R are obtained for the light ray which is incident on a spherical surface. The relation obtained is valid. This is the important thing. The relation obtained is valid irrespective of the surface which you are talking about is convex or concave, and the image that is obtained is real or virtual. Expressions for the two principal foci are obtained, and the question session is containing the following questions. Number 1, state the Gaussian relation connecting U, V and R. Whether the above relation can be used both for convex and concave surfaces. Give the expressions for the two principal foci. With this, we come to the end of the lecture number 2, and in the lectures to come, we will see the other things which are to be covered as per the syllabus. Thank you.